early morning, everybody. Today I'm going to talk to you about my lab number 2, Projectile and Two-Dimensional Motion by David Presley.
Introduction to the lab. Understanding the goals of Lab 2. Lab 2 is meant to test the principles of projectile motion and Newton's second law. We will learn about how to account for error, learn how to use tracker and glow script to track an object and predict future positions, and we will learn some new forces, like gravitational force and coefficient of drag, and how they will impact our overall motion.
Some of the formulas we'll be needing to use today are Newton's second law, our kinematics equation from last experiment, our velocity update formula derived from kinematics, and our position update formula. Some of the equations that we need to remember are all 3 of the universal gravitational equations and our drag and air resistance, with the negative in that equation being because it's always an opposing force, just like friction. Here are some of the materials that we needed for this experiment: a distance measuring device, a paper ball, a laptop that can run tracker and glow script, a TI-84, and an incredibly accurate mouse to measure our center mass. Our system is the paper ball and our surroundings is everything else. Our surroundings will have a force impact on our system that we will be calculating in this experiment. Lab procedure. And here are the steps to my experiment, which I will not be explaining for the sake of time. So please pause the video if you would like to see these in more depth. Here is my lab's video of our experiment. You can see that we tried to estimate the center of mass by clicking in the middle of our paper ball, and our axes, calibration stick, and meter stick are all aligned and shown. Results and discussion topics. These are some of our initial conditions for our test. Our experimental data is all written on the left-hand side, and one thing of note as a difference between the glow script data with drag and without drag is that the drag constant is in our top right little square here, and we will be using that drag constant in our drag equation later on. Some important equations to remember are our velocity update formula derived from Newton's second law, and also our position update formula, which we are using in all of our iteration steps throughout the experiment. You'll notice that in our important code equations, the with drag has an FD definition, which is our drag equation, and our FNet takes that into account by adding in FD next to work, which our without drag equation does not do. Also, for arrow scales, we have that there is a drag arrow included in our without drag and not a drag arrow included in our with drag. And here are our coding results, the glow script drag versus the glow script no drag, with the lines being indicated in red and blue. The lines do not perfectly overlap, and the drag covers slightly less distance over the time of the experiment, meaning that drag must influence our velocity. And in my coding results, this trend is also emphasized, but it's hard to see because of the overlapping lines with the incredibly small values. My conclusions and takeaways for this experiment are that as time progressed, the combined drag plus gravity force slowed down the red line over distance covered. This is why the red line ends sooner than the blue line, because it was subjected to drag forces as well. Also, both x/y glow script with drag and x/y glow script without drag underestimate the actual x/y tracker experiment model. This suggests there may have been other forces present that accelerate the ball toward the ground faster. Some major errors include the incalculable amount of forces that were also present, a drag coefficient calculation that could be incorrect because air resistance is not constant. The center mass is also calculated by clicking in the center of a paper ball, and while I think my accuracy improved this time, it can still never be perfect. Our discussion questions were, do any of your models predict a terminal velocity? None of them do. In my x versus y graph at the end of the experiment, there is still a slope to be seen. We would likely have to experiment from a much higher location or decrease ball mass in order to achieve terminal velocity. If we threw the ball upwards with the same velocity magnitude, so we just flipped the y signs, there wasn't a huge difference because my velocity component in the y direction was quite small. However, we still throw the ball slightly upwards in the y direction, so it will take slightly longer to hit the ground than our initial experiment. Here are the 2 graphs from my last discussion point. The 2 graphs are basically indistinguishable, but I promise the numbers on the left are larger and therefore the ball when thrown upwards covers more distance than my original glow script drag versus no drag graph.